Okay, now we will see what happens when we add support to the tunnel. So if you look at the file called hybrid.dat, here's where we are going to run the same model, but try installing some bolts. So the first part is the same. We restore the initial state. We excavate the first 4 meters. We solve. And then we install the bolts. Here's the command for installing bolts down here in 22 and 23. Of course, there are different types of support. And in this example, we're using the hybrid bolts. So the command looks like this: struct hybrid create by line. And then you give a starting position, X, Y, Z, and a finishing position, X, Y, Z, and the number of segments. So the number of segments that make up the bolt, you can think of this like the zones that make up your volume. The more segments you have, the more accurate will be your solution. However, there's not really much point in having significantly more segments than there are zones across the length. Recall that when we zoned this model, we used the minimum edge length was 2. We're making these bolts here. The length, I'll talk about this in a minute, but the length is 4, and they're in 4 segments. So each segment is about 1 meter, and that will be plenty accurate enough for this example. Now you can just type in these commands one by one to create multiple bolts. What we're doing here instead is using a fish function. And so we know that we have a circular tunnel. It's relatively easy to figure out the starting coordinate and the ending coordinate of some points that will create radial bolts. In this case, we're assuming that we want 5 bolts around the top part of the tunnel. We know the radius of the tunnel. We know the length of the bolts. We can use some sines and cosines here to work out the starting coordinates and ending coordinates to create these 5 bolts. So it's a little fish function here, and the input is the Y position. So we've got an array of 5 bolts. All of them have a Y coordinate of -8 the first time, and then we can use the same function to create another layer of bolts, and another layer of bolts, and another layer of bolts, and so on. Okay, I'm just going to set this running, and then we can continue talking about it. So the first part is, again, restoring the initial state, excavating the first 4 meters, solving. This function is called to install the bolts, and then we assign the properties. So for properties, struct hybrid property, this line 30 here is the properties related to the actual steel bolt itself. You can think of it as maybe rebar or some other kind of steel component that makes up the stiff part of the bolt. So this is the cross-sectional area of the steel part, the Young's modulus of the steel part. Remember, this is in megapascals, so this is pretty stiff. And then you give a tension force for the steel part. Okay, and again, this would be in meganewtons. Then line 31 here, we're giving properties related to the grout. Now, remember, there might not actually be grout if you're modeling split sets or something like that, but there is some potential movement between the steel bolt itself and the rock. And then there's some stiffness associated with that interface. So that it's a shear stiffness, which dictates how easy it is for that bolt to move relative to the rock. And then there's also a strength above which, if the shear force exceeds this cohesion, then it becomes perfectly plastic and will not be able to resist any more shear force. So we've got properties related to the steel part, properties related to the grout, and then you also have properties related to the dowels. Now recall with the hybrid bolts, every time a bolt crosses a joint, it will create what we're calling a dowel, and it's really just a shear spring that resists the shearing, of the joint. And so these little dowels need to have a stiffness. Again, this is in like meganewtons, a yield. And then, so when it hits this yield, it again goes perfectly plastic. It will continue to resist shearing, but it won't resist any more shearing. It resist increases in force. It's perfectly plastic. You can also specify a failure strain. So if you reach this amount of shear strain, then you have catastrophic failure, and it doesn't resist anything, and your bolt's basically broken. If you're using this strain, you need to also give an active length, because recall that strain is change in length over length. So we need to have some sort of reference length in order to calculate the strain. You can think of this dowel active length as the part that gets activated when the shearing of the joint occurs. If you picture in your head a bolt crossing a joint and the joint shearing, the bolt will form a little S shape. And the extent of that S shape is really the dowel active length here. So in this case, we're saying 0.1 meters. And then we're saving it. So what happens here is we excavate first. We can't install bolts without excavating, obviously. So we excavate first, then we install the bolts. The bolts don't do anything, right? We just installed them. They don't hold any load until we do more excavation, at which time then they start to take load. So we put the bolts in, we save it, then we excavate the next 4 meters here. We solve that. Then we install the next round of bolts. We call the same fish function, but now we're saying y equals -4 instead of y equals -8. So we get another round of bolts, and we have to give the properties for the new bolts that we just installed. So here, see, when we're assigning the properties, we're saying range position y -5 to -3, which ensures that we're only assigning the properties to the new bolts that we installed. It's not strictly necessary. If you reassign the properties to the existing bolts, it's not a disaster. But if you want to be clear about what you're doing here, you can say, give a range to only install the new properties. What we could have done here, which would be slightly more intelligent, would have been to give the properties with the installation of the bolts here in the fish function. Then we wouldn't need to copy and paste these property assignment commands every time. We could have just put it in the fish function here, and it would have been easier. So anyway, we've run this file. We've excavated 2 sections of tunnel and installed 2 sections of bolts. We can go and look at we can look at a bolt plot. I've given it to you, but instead let's create a plot from scratch just so I can show you how to do it. So if I go up here and make a new plot, let's call it bolts 2. As always, I go to the plus and I add. Now I can look under structural elements. Here's all the different structural elements. And what we did was we created hybrid bolts. So if I double click on hybrid, you can see here the 2 layers of bolts at different Y locations. Each of them has a different color because each was created with a different command. So we've got a total of 10 bolts here. It's a little bit hard to see what's going on. It would be nice to see maybe the tunnel. So what we can do here is add the blocks. So we can see the tunnel, but now we can't see the bolts because the blocks are on top of them. You could just make these blocks transparent. It's still a little bit hard to see. So what we do here instead is a little trick to help you visualize what's going on. I didn't talk about it in detail yet, but if you go back to the unsupported data file, you will see that we use the command block delete. What this does is it completely deletes the blocks. They're gone forever. Obviously, they have no effect on the model. You can't bring them back. They're basically gone. That's fine. But imagine a situation where maybe you were doing some excavation and then you wanted to backfill. This is very common in mining. In that case, you use a different command. So if you look at what we did in the hybrid data file, instead of saying block delete, we said block excavate. What this does is it nullifies the effect of the blocks, so they're not participating in the calculations at all. But it is possible to bring them back in the future as potentially backfill. So the blocks are actually still there in memory. They're not having any effect on any of the calculations, but it is possible to bring them back, and it is possible to plot them. So we're not doing backfill in this example, but I use the block excavate so that we can actually plot them. So if I go back to my bolts 2 plot, so here I'm looking at the blocks. If you look at the attributes, there's a checkbox here for excavations. And if you check that, it will show only the blocks that have actually been excavated. And this is super handy for plots like this, when you want to see the tunnel, and you want to see the bolts and where they are in relation to the tunnel. There are other ways you could do this. You could plot, you could somehow identify the faces of the tunnel and just plot those faces, and we'll show that in a little bit. But this is a super easy way to do what you want to do. So here's the bolts, here's the tunnel. Now recall, every time we draw one of these bolts and it crosses a joint, it creates one of these dowels. And so we can also plot that. So if I go up to this plus, under the structural elements, you can choose dowel. Got all these little dowels here. It's a little bit hard to see because they're on top of the bolts. So we can just hide the bolts for now. Here's all the little dowels. And by default, they plot at the actual active length that you specified. So remember we specified the active length is 10 centimeters. So we've got all these little 10 centimeter pieces, and they plot perpendicular to the joint that they're crossing. So you get some idea of the orientation of the spring that's acting here. You make these a little bit bigger. It's a bit hard, again, it's a bit hard to see them. If I click on my dowel group of element and I go into attributes and I go to dowel, I can double the length scale. So now it's just showing them 20 centimeters long instead of 10 centimeters long. And I can double the width scale. Right, so now it's a little bit easier to see these dowels. So you can see how they've been created everywhere that bolt crosses the joint. You can see how there's a regular pattern here. Note that they actually get created even when they cross joined joints. It turns out that they don't really do anything because the joints are joined and you don't have any shearing, but they do get created there. Okay, so the next part, if we go to hybrid2.dat, we restore the existing state. And now what we're doing, so far we've been excavating 4 meters at a time. This is kind of just a way to speed up the analysis. In reality, you're probably excavating 1 meter at a time, or maybe even less. But let's pretend we want to continue on doing 4 meters at a time. We know that if we excavate this 4 meters and try to solve it, that wedge is going to fall out of the roof. And again, in reality, you're probably excavating maybe 1 meter at a time. But let's pretend we don't want to do that. We can simulate a more gradual excavation by, instead of deleting all the blocks in one shot, we sort of gradually reduce the effect of those blocks. And we do this with this block relax command. We've probably seen this before, depending on what order you've been doing these tutorials in. But the way this block relax command works is it actually excavates the blocks, works out the reaction forces required to prevent movement of the blocks outside of the tunnel. Those reaction forces are applied to the surface of the tunnel and then gradually reduced. Okay? So you say block relaxed, and then you specify how you want those reaction forces to be reduced. And I'm going to say I want them to be reduced in a linear manner over 1,000 steps. It doesn't have to be linear. If you look at the help for block relax, you can write your own fish function and relax it any way you like. There's also a nonlinear way to do it so that the reaction force is reduced from 1 to 0 in a nonlinear manner, and so on. In this case, we'll just do the simplest thing, which is reducing the reaction forces linearly from the maximum to the minimum over 1,000 steps. But note here, by default, the minimum is 0, so the reaction forces go to 0. In this case, we're specifying a minimum of 0.5. So that we're reducing the reaction forces by a factor of 2, so that there's still support being applied to the surface of the tunnel. So hopefully that wedge will not fall on our heads. And when we still got a little bit of support here, we can install the next round of bolts. So first we're actually deleting those reaction forces, but we're not cycling, so it's okay. Nothing will happen really. Then we install the next round of bolts. And this will continue to relax because now we've removed those reaction forces. The tunnel will continue to move inwards. But hopefully the bolts will now be able to take some of that load and prevent that wedge from falling on our head. So we can run this. It restores the existing state with 2 bolts. It sets up these reaction forces. You can see here in the console, total reactions, and it tells you X, Y, and Z component of reaction forces that have been applied. It's creating some more bolts here. Again, calling the same fish function, but now we're installing bolts at Y equals 0, specifying properties, and then solving again. So we can go back and look at our bolt plot while this is solving. Let's turn off the dowels and put the bolts back on. So instead of just looking at the colors, we could change the label to contour. It defaults to displacement, but usually what's more interesting is something like axial force. So you can see the forces in these bolts. It's pretty low, except for this one bolt here, which is the guy that's holding up that wedge. And then you get a pretty high axial force here. Remember, this is mega newtons. As a fun trick here, maybe you don't like seeing this E-1, E-2. You'd rather just see numbers. If you go into your plot legend, your labels, you can change it from scientific to decimal. Maybe you want 3 decimal places, but so now you don't see that scientific notation. Anyway, that's just a neat trick. So here's our bolts doing some job. We can go back to our block plot and look at displacements. So you can see that wedge is still moving. I've still got that deformation exaggeration of 20 on here. So the movement isn't a lot. We're looking at about 3.5 millimeters here. So the bolt appears to be doing its job. You can verify that further by looking at the history. So here's the history of a point that we measured in the roof. First stage of excavation, a little bit. Second stage of excavation, a little bit. Third stage of excavation, remember we relaxed without any support. So we do get a fair amount of displacement here. It kind of bounces back up again. We have this support. Eventually it comes to some sort of equilibrium, again, around about 3 millimeters of displacement, so not a lot. So we can be fairly confident that this is now stable and that the bolts have done the job that we were hoping they were going to do. One last thing here we can look at just for fun. If we go back to the bolt plot, you can look at the dowels. You can change that label to contour and change that to shear force. So you can see the shear forces in the dowels. And like I said, a lot of these are crossing joined joints, so the shear force is negligible. But where they're crossing real joints, you can see that there's fairly significant shear force being taken by these dowels, resisting the shear of those joints. Okay, so that's an example of how to use the bolts. And then I've also given you here some data files to specify liners instead of bolts. So another way that you could try and support the roof here instead of using bolts is you could put in liners. So if we look at liner.dat, there's a slight extra wrinkle here. So lines 2, 10, and 12, we've already seen. We're restoring the initial, we're excavating 4 meters, and we're solving. Before we excavate, we want to identify the faces on the surface of the tunnel so that we can then attach a liner to those faces. So an easy way to do that, there's several ways to do it, but one easy way to do it is to find all of the faces that are on the intersection between 2 different groups. So remember that we called the middle of the tunnel group tunnel. We called outside of the tunnel group rock. So all of the faces that exist in between the rock and the tunnel, we can give them a name. We can give them a face group name. So here we say block face group, tunnel surface, range, group, intersection, rock tunnel. So all the faces that exist at the intersection between the rock blocks and the tunnel blocks will get this group name tunnel surface. And we use that later when we're creating liners. All right, let's just run this. So yeah, group tunnel surface assigned to 948 faces. Now we excavate the first 4 meters, we solve. This should be exactly the same as what we saw before. Here we're creating a liner. If you know the faces that you are applying the liner to, this is super easy. You just say struct liner create by block face, range group, and you give the group name. And in this case, we only need to do the first 4 meters. So we also say range position Y -10 to -6. You need to give liner properties, struct liner property, isotropic. So remember in the slides I showed how you can have, remember in the slides I showed that you can have nonlinear liners that can potentially fail. So you could have more Coulomb liners and von Mies liners and things like that. In this case, we're assuming they're elastic. So what you say is you say struct liner prop isotropic because they're Young's modulus, a Poisson's ratio, and a thickness. And that part is super easy. It's just like an elastic material. 2 more parameters here required to account for the coupling between the liner and the rock. So there's and remember that the coupling between the liner and the rock is really just contacts. And just like the contacts between blocks, you have a normal stiffness, a shear stiffness, a normal strength, and a shear strength. So we give a shear stiffness, a shear friction, a shear cohesion, a normal stiffness, and basically a tensile yield for the normal direction. So we specify the properties. And again, this is like the bolts. We excavate first, then apply the liner. The liner doesn't do anything until we start excavating again. So we excavate the next 4 meters. Now the liner starts taking load. We solve it again. We install the next round of liners. Same command exactly as before, except now we're using different range and Y coordinates. Again, we have to specify the properties for the new section. I could have given a range here. If I just re-specify the properties of the range that already exists, it doesn't really matter. I'm saving that. So we can have a look at that. Again, there's actually, I don't think there's a plot here, so we'll create a new one. So let's go. New plot. Let's call it liner. Oh, maybe there's one already called liner. Let's call it liner 2. I go to plus. Under structural elements, they can now choose liner. Here's the liners. You can see sold it in 2 sections. The first 4 meters and then the next 4 meters. So they have different IDs. As with everything, you can change the label to contour. Again, it defaults to displacement, but maybe you want to look at something like elastic stress or, and then again, there's all these different components. It starts to get a little bit complicated when you are doing interpretation for the liners. There's stress resultants and things like that. I'm not going to go into that as part of this class. You can certainly read about it in the manual. Interesting though, look, the stress of part 2 here is 0 because, like I said, we installed the liner, but we haven't done any more excavation, so it's not taking any load. Let's just look at, oh, look, you can see maximum principle, another thing. Let's change this back to displacement of node, but instead of showing X, let's just show magnitude. So again, magnitude of displacement in round 2 here is 0. In round 1, something that's not 0. Okay, same thing we did before. We're going to apply reaction forces, reduce them gradually to 50%, simulating perhaps a sort of gradual excavation of the tunnel, or maybe an excavation of a tunnel with some temporary support. We delete those reaction forces and we apply the last range of the tunnel, the last range of the support, I should say. And again, we assign the properties, and again, we do a solve. In this case, I've actually specified a limit here. I wasn't necessarily sure that it would solve. So anyway, here it goes. We can look at our block displacement and convince ourselves that everything's okay. So again, you can see this wedge moving a little bit, but we're still talking about millimeters here. This is, it looks like the liner is going to work, and that this will not fail. We can look at the histories to try and convince ourselves of that. So here's the same sort of behavior we saw before. We get this relatively large decrease and a bit of a bounce, and now it's just smoothing out. We can go and look at the liners. This is a pretty coarse model. These plots are not beautiful. There you go, it solved. So it did solve in 3,700. I didn't need that cycle 10,000 there as a safety mechanism. But anyway, you can look at the displacements. You can see the biggest displacement here is right where the wedge is. It's pushing down on this liner. But the displacement is still on the order of a couple of millimeters, so it's not a catastrophe. So here you can see that the liners or the bolts will work at restraining this wedge. There's a whole lot of other complexity when it comes to structural elements. For example, how to attach the cables to the liners and how to attach the liners to each other, the different segments and so on. That's something for a more advanced class. And I will stop it here for this one. Thanks for joining.